My name is Brian Searle, and I'm from Proteomics Software, and would like to give you an introduction to analyzing mass spectrometry data using data-independent acquisition. And I'd like to start this off with kind of a little gimmicky idea. But if you were trying to ask the question, is a specific book like Harry Potter in a library, you might go through and pull a whole bunch of books off the shelf, maybe starting with the biggest first, and pulling them out onto a cart and then looking at what they were. So you might say that one of them was Moby Dick, one of them was Pride and Prejudice, one was War and Peace, and maybe there was no Harry Potter to be found. And so you wouldn't necessarily go back and say, there's actually no Harry Potter in the library. The better way to do this would be to look using the Dewey Decimal System for the spot in the library corresponding to J.K. Rowling, look for Harry Potter and pull down that book and see if it was actually there or not. Now, this is obviously hyperbolic relative to data-dependent acquisition, but I think this point is pretty important in that failure to detect a peptide with DDA is not necessarily a proxy for its absence or its lack of abundance. And that really thinking about data acquisition using data-independent methods such as PRM or DIA are much better solutions for this sort of problem. So PRMs, or parallel reaction monitoring strategies, are great, but what if you wanted to measure an entire proteome? And is it possible to actually target every single peptide? And the answer is, it sort of is, but there are definitely some caveats that you need to take along with that. So here we're going to talk about a bunch of these caveats and compromises that are required to make DIA like PRM, or analyze it from a PRM perspective. We're going to talk a little bit about the many different approaches to acquiring DIA data, and then we're going to talk a bit about the benefits of DIA in certain types of experiments. Finally, we'll chat about how to make the best types of choices for acquiring DIA data sets. So how is DIA different than PRM or DDA? So with DDA, you might acquire instrument-targeted windows around peptides of 2MZ wide windows where you would collect an MS2 spectrum and detect a peptide from that spectrum. Now, you'll acquire them in an instrument-targeted way, so you'll only get one fragment ion scan or one MS2 per peptide, but you will be able to potentially identify a proteome's worth of peptides. One problem with that is that because you're using MS2s for detection only, you have to use precursor intensities for quantitation. PRM is a bit different. Instead of letting the instrument target peptides, you tell it which peptides to actually target, and it scans only for those peptides. But it does it in such a regular way that you can do quantitation using fragment ion intensities. Both of these strategies use tight precursor tolerances that reject a lot of the interference, so we're talking 2MZ wide targeted windows. DIA, on the other hand, tries to do a bit of both. It tries to do comprehensive detection as well as the sort of selective quantitation that you get with fragment ions, but at a compromise. With DIA, the only way to scan across an entire proteome's worth of peptides using untargeted windows is to make them pretty large. So we're talking 12 to 24 MZ wide targeted windows, untargeted windows. And that makes it much more complicated to do detection, and thus it's not quite as comprehensive, and the quantitation is more challenging because of all of the interference from these wider windows. That said, we are able to achieve fragment level quantitation similar to with PRM. So what types of DIA experiments are typically used? Early on, in the mid-2000s, people have been talking about parallel reaction monitoring as a strategy to make SRM-style acquisition available on Orbitrap and TOF mass spectrometers. So the strategy here is to acquire usually a precursor scan followed by a series of fragment ion scans that were pre-programmed by the person wanting to collect data. And so for the first duty cycle, they might acquire a precursor scan, and then 4 fragment ion scans, and then in the next duty cycle, they'll acquire a second precursor scan, and the same 4 fragment ion scans. These are going to be repeated, but because they are repeated, we're able to draw what are called chromatograms, or measures of those fragment ions across time. So early in the mid-2000s, Waters actually pioneered this strategy of doing high-low mass spectrometry, or MS to the E. And here the idea was to collect a precursor scan again for all of the peptides that are being eluted at the same time. So this might be in the order of hundreds of peptides eluting at the same time. And then fragment all of them simultaneously to acquire a fragment scan. Now this fragment scan is going to be considerably more complex than the parallel reaction monitoring scans, because instead of monitoring one peptide, we're trying to monitor literally all of the peptides that are eluting at the same time. And so these scans are made up of hundreds of peptides potentially. And then the strategy was to alternate this, acquire a precursor scan followed by a fragment scan, followed by a precursor scan, followed by a fragment scan. One big advantage of this strategy is because you are acquiring regular enough fragment scans, and we're talking quite frequent, as in sub-second scans, you were able to do quantitation using fragment ions on their own, and it was able to measure across the entire precursor MZ range. However, the strategy, because of the high multiplexing involved and the fact that you were acquiring data on so many peptides simultaneously, there's a huge reliance on computer programs to effectively deconvolute the peptide signals to make peptide detections. So another strategy that came up in the late 2000s was the Pacific strategy by Dave Goodlet's lab. And this took a somewhat different approach, or perhaps the opposite approach. And it focused on, instead of doing these very wide window DIA scans, they focused on these narrow window DIA scans. They were a lot more like DDA in that respect. And so you would have these pretty narrow DIA scans that were regularly, sequentially acquired, but because they were so narrow, you weren't able to map the entire proteome in a regular way. And so what you ended up doing was acquiring a precursor scan followed by a few fragment ion scans in order, and then another precursor scan, and then those next, an additional set of fragment ion scans in order. The advantage of this strategy was that you'd be able to have much more narrow precursor isolation windows, but realistically you'd end up analyzing data such that you're requiring a fragment ion scan, if at best, only once across the shape of the peptide peak. So consequently, you could only do fragment ion-based quantitation, and precursor-based quantitation, and that fragment ions were really just used for detection only. And similarly, you were actually only limited to being able to work with a pretty narrow precursor MZ range, or using a lot of experiments to cover the entire precursor isolation range that you might be interested in. That said, these samples, or these acquisitions, were simple enough in terms of their MS2 spectra that you could use a normal database search engine such as Sequest or Mascot to actually do the detection of peptides out of these scans. So about 5 years ago, the Ebersol lab came up with an alternate strategy that was kind of a hybrid between these two ideas, called wide window DIA, or swath-style DIA. And the idea here was to, again, collect a precursor scan across a somewhat more narrow range, so maybe 400 to 1,000 MZ or 400 to 1,200 MZ, and acquire a wide window fragment scan. So in this case, instead of having it be the entire width, like with MSE, or a 2 MZ wide fragment ion scan, as with Pacific, this strategy would acquire usually 25 MZ wide windows and acquire them regularly enough so that they could scan across the entire range. And then, once again, you would collect another precursor scan and that same batch of fragment ion scans. The advantage here was that you could do quantitation using these regular fragment scans since you acquired each precursor isolation window once per duty cycle, but at the same time, still being able to measure an entire proteome's worth of data in a single experiment. To compare these types of spectra to the MSE spectra, MSE again would be very complex because you would be trying to measure hundreds of peptides potentially eluting at the same time, while with DIA you actually only be measuring a handful of peptides, potentially 5 or 10 or 15 peptides at the same time. And while these spectra were still very complex, they were at least interpretable using some different sorts of strategies. So again, quantitation was done with fragment ions, and that you would get frequent enough scans to be able to measure the shape of the peak, but usually you'd have to measure a compromised precursor MZ range, so something like 400 to 1,000 instead of the entire precursor range. This approach was somewhat less reliant on deconvolution than the MSE approach, but at the same time it was pretty complicated, still far too complicated for a normal database search engine like Mascot or Sequest. However, now we're starting to make data that looks a little bit like PRMs in terms of its quantitative readout. So what do these DIA experiments look like? Now, I was showing you some toy examples before, but generally, to give you an idea as to what a normal DIA experiment would be, you'd acquire a precursor scan again from 400 to 1,000 and fragment ion scans in repeated sequential order across that entire range. Here I'm showing you 25 by 24 MZ wide window ranges to match that entire precursor isolation with. And then you would skip over and do it again, acquire the same precursor scan and a bunch of fragment ion scans. The idea would be to acquire precursor scans and fragment ion scans that were close enough in time such that you could start to map the shape of a peak, at least with 6 to 8 or 10 points across the peak. So typically you would want to try to get the time down to 2 or 3 seconds between fragment ion scans or repeated fragment ion scans. Now, I'm going to collapse all of those fragment ion scans to show you a bunch of these repeated duty cycles, see what they look like. So if we isolate one of these fragment ion scans, say this one in yellow, from 784 to 808 MZ, we might look for a particular peptide that falls around 790. So for this specific peptide, you might look at a fragment ion scan and see all of the fragment ions that are associated with it, all the B and Y ions that make sense for that particular peptide. But with DIA, we actually acquire this data regularly in a repeated fashion. So instead of measuring one fragment ion scan, we're measuring it across time. And we can see, as a result, the shape of the peak, because all of these fragment ions should rise and fall with each other. And if they don't rise and fall, then that indicates some kind of interference, or it indicates that those fragment ions don't actually belong to the peptide we're interested in looking at. So this kind of makes it kind of clear what data we're looking at. So it's really, instead of looking at sequencing MS2s individually, we're really looking at this data as three-dimensional data, where we've got one axis that's mass over charge, and we've got another axis that's retention time, and we're filling in this block in the third dimension intensity. And so again, if you were to look at it in the MZ space, you would see these fragment ions that were associated with individual peptides. But if you looked at it simplified on the retention time axis, you would actually see and extracted that fragment ion specific to a particular peptide, you would see these fragment ions rise and fall with respect to the peptide that you were measuring. And this is what is called a chromatogram, or a chromatographic view. Now, there are a couple of caveats to acquiring DIA data. and we should talk about these before we get too much further in. And the fact is, you're going to acquire fragment ions for peptides, but those peptides aren't necessarily going to fit in the center of the window. More importantly, they're also not going to necessarily be all of the same charge state. So with DIA, you have to make an assumption as to what charge state your peptides are. Since the majority of peptides are +2 peptides, we typically tell the instrument to set collision energy optimization for +2 to fragment +2 peptides. But not all peptides are +2 peptides. +3 peptides and +4 peptides won't necessarily have their collision energies optimized to give them the best fragmentation. So as we were talking about earlier, you are co-fragmenting several peptides simultaneously, and you're trying to use the shape of the fragment ions over time to be able to discern which fragment ions came from which peptides individually. Finally, there are what we call edge effects based off of transmission efficiency from the quadrupole number 1. And so in Q1, typically you pass through peptides, or you tell the mass spectrometer to pass through peptides from 784 to 808, but that's not necessarily how the quad works. It is most efficient in the center of that mass range and maybe less efficient towards the wings. So you end up potentially getting these edge effects that can suppress signal if the peptides are on the edge of the window, say, for example, this red peptide right here. So that said, let's start to look at some of this data. So this is a particular peptide from superoxide dismutase. In humans, extracted, all of the fragment ions have been extracted over the entire retention time, so from 0 to 135 minutes. And so it's pretty hard to tell which peak here represents the right peptide. But it's this one right here. And so if I look at the fragment ions close up, I can see that all of the fragment ions collude here, as expected, to represent this peptide, whereas in the other places around this peptide, they usually typically don't collude. So this peptide is pretty easy to see that this is the correct detection because you get all of these nice clear fragmentation patterns that collude together. Now that's not always necessarily the case. Here is another peptide from the same protein, superoxide dismutase, in the same sample. Now this peptide is a little harder to pick out. And if I zoom into some range into this mixture, I could see that there are multiple signals that might appear like individual peptides and that they don't necessarily look very clean. And so one question might be, is this peptide that I'm interested in looking at, is it the peptide on the left over here, or is it the peptide on the right? The answer actually is that it is the peptide on the right. But how do I know that? And realistically, the only way to be able to figure stuff like this out, or peptides that are sort of complicated in this way, is to use approaches that know something about the peptide fragmentation that you're expecting to see. So one way to deal with that is to do library searching. So typically with a library, you might acquire an MS2 fragmentation spectrum from DDA experiments acquired either in your lab or in someone else's lab, and compare them to the fragmentation patterns that you might see in your sample. And in this particular case, it's actually fairly easy to make the detection because I see a really nice high Y8 and Y9 ion, and potentially a Y2 ion. I see the Y10, Y11, Y12 in a nice ladder, and those are also the next highest ions that I would expect to see. So given this, I'm pretty confident that this is the correct peptide. But there are some idiosyncrasies that you might notice. So for example, here in my library spectrum, Y8 is higher than Y9, while in my acquired spectrum, that's not necessarily the case. Now, part of this could be because +3 peptides, again, are fragmenting somewhat different in DIA than they are in DDA, just due to those tuned collision energies. But it can also be for other reasons, too, and this is one of those cases. So if I try to extract that specific peptide out of the DIA data, this is the MS2 fragmentation spectrum at the apex of that peak. There are two things that I think are important to know. One is that, as it's pretty clear, these spectra that we're trying to dig these peptides out of are actually fairly complex MS2s. And consequently, it's actually a bit difficult to make the determination of the peptide. And that using these chromatograms, that's really the only way to be able to figure out that this is the true MS2, or this is the true peptide that represents this at the apex of this MS2 fragmentation data set. So here, one of the things that you can see is that at the apex of the peak, Y8 actually is higher than Y9. And the reason of this is because of interference. So we can actually see that Y9 fragment ion actually shows quite a bit of interference and is shifted over for this particular peptide. But there are enough fragment ions that actually fit the shape of the peak, those are in green here, that actually indicate that we've detected the correct peptide. And so from this kind of plot, it's important for whatever kind of computer software we're using to be able to determine the wheat from the chaff, as it were, and call the green peaks as being part of this peptide, and that the yellow and red are peaks that have been interfered with in some way. So this is actually how computer programs analyze this type of data nowadays with this peptide-centric approach. So looking across an entire chromatogram, we might extract out all of the fragment ions that are associated with it, and we'll score them over time. And this is a bit different than a spectrum-centric scoring approach that you would typically do with DDA search engines that analyze for each individual spectrum what are the best peptide matches. Here we're trying to take a single peptide and see where is the best evidence for this peptide being in the sample, and does that meet a reasonable criteria. So if I look at the apex of that peak in time, so where that peptide scores highest in time, that will give me a reasonable place to look for where I should find that peptide. And so in this particular case, it actually shows the fragmentation pattern for that peptide nicely. So you might wonder, why would we recommend that you consider DIA at all if there are all of these caveats to doing the data acquisition? And I think you need to consider this from multiple perspectives. The first is, why is DIA potentially better than SRMs or PRMs? So in an SRM or a PRM experiment, you might generate a whole bunch of hypotheses for which pathways you want to go after. Say, for example, you want to target all of the peptides that are interesting in the mTOR pathway. And from that, you might pick out a bunch of peptides that you want to select for monitoring, and then purchase them potentially, and then finally acquire some initial scheduling data to do some RT analysis, and then refine to determine which transitions are going to best represent that peptide. All of this requires data acquisition. And then finally, you'll get down to actually acquiring your quantitative data on the experiment that you care about. Once you've done that, you might draw some hypotheses, and then decide that you actually needed to pick some different peptides to monitor the pathway that you wanted to go through. And then you got to go back to the drawing board again, pick some more peptides, do some more scheduling, purchase them, and then do some more refinement and additional data acquisition on top of that. And there might be several rounds of this. With DIA, the promise of DIA comes with this sort of data acquisition first approach. So here, instead of generating a hypothesis first, you can acquire data globally across an entire proteome, and then ask the question, well, let's look for a bunch of mTOR peptides and see if anything makes sense. So you might select those peptides out, extract them, and do the transition refinement all in silico, and then generate a hypothesis and decide if you wanted to extract some more peptides. But you don't have to go back to the raw samples. You don't have to go back to reacquire the data again. So in this regard, if you can acquire pretty close to PRM level quantitative data with DIA, then this is potentially a big advantage. The strongest advantage of DIA over DDA is really in its reproducibility. Because you're acquiring the same repeated scans over and over again, we find that DIA tends to detect the same peptides from one replicate to the next, and this improves the quantitation accuracy as well as the detection accuracy. So instead of seeing only 60% of peptides repeat over 3 replicates, we see something closer to 75% of peptides repeat over replicates. Along those same lines, we find that the quantitative accuracy is substantially higher as well. And so with this data set acquired by my colleague Lindsay Pino, I'm mapping coefficient of variation between triplicate analyses in yeast around the bottom and then the number of peptides across on the y-axis. And after some automated transition refinement and filtering based off of peptides per protein, we actually find that the coefficient of variation, or the variance amongst the peptide measurements in these replicates, actually is pretty close to what we see with PRM or SRM. We might not necessarily have the sensitivity of those approaches, but at least the accuracy of the measurements is pretty good, such that we might get a median CV of less than 10%. And this, as long as we've done some pretty strong transition refinement and automated computer analysis, we can typically get very robust quantitative data sets to do these measurements from. So enough talking about why you might want to acquire DIA. Let's talk about how you could acquire DIA. And the best place to start is perhaps with this Nature Protocols paper published by Jarrett Egertson, where he details how to set up an instrument and acquire data and do the analysis. We also have an additional document that provides starting points for where you might want to set your instrument to start acquiring data for DIA methods, the methods that we discussed here in this talk. So let's talk about some of the things you need to think about when acquiring DIA. The first thing is, we've talked repeatedly about needing to get enough points across the peak. Why do we really need 6 to 8 points across the peak? Here I'm showing you a chromatogram from a peptide that was acquired using only 5 points. And I think we could all agree that this is a lousy peptide to do quantitative measurements. And the reason why is because almost every approach that's doing quantitation for proteomics with targeted approaches, from Skyline to OpenSWAT to Scaffold DIA, are going to do what we call trapezoidal integration. And the idea here is you're measuring from point to point these trapezoids and integrating that area. And you're hoping that the error that I'm pointing out here is going to cancel out. And that's going to only be the case if you've acquired enough data points. So I'm showing you here at the bottom of this axis the number of points across the peak, and on the y-axis the percent deviation in area for a wide range of peptides or measurements. And we find that if we're talking about peptides measured in the 6 to 8 points across the peak, we usually see on the order of 5% deviation at worst in terms of the actual quantitative measurements themselves. And this is, again, not error from technical variability or biological variability. This is error only from doing these trapezoidal measurements. Now, what we find is the best way to avoid measuring lower than 6 points across the peak is actually to try to tune the instrument so that we're working with about 10 points across the peak. This is mainly because peptides that elute at the beginning of the chromatogram or at the end of the chromatogram tend to be narrower than those in the middle. So another question you might ask is, why are we talking about 400 to 1,000 MC? And so here I'm plotting at the bottom axis of this the precursor mass to charge for a bunch of peptides across big spectrum libraries, and the number of identified peptides on the y-axis. And as you can see, there's a shape to this curve where you really get the most number of peptides in this 400 to 1,000 MZ range. And that's the range that I think is worth targeting the best. That said, there might be some reasons why you might want to target from 400 to 900 or from 500 to 900 and try to optimize your detection rates in those ranges. To make this a little bit more concrete, if we're talking about narrow window DIA data, that's something that's analogous to DBA with 2 MZ wide isolation, and you increase the mass to charge range in this time, you actually get more peptides detected. So as you're going from 500 to 900 or 400 to 900 or 400 to 1,000, that increases all the way up to 400 to 1,200. However, that's not really how we acquire DIA data. Typically, we acquire these wide window data sets where you have to compromise on window size to match the precursor isolation range that you're interested in. So from 500 to 900, you might be able to acquire 50 by 8 MZ wide windows, while at 400 to 1200, you might have to acquire 50, 16 MZ wide windows. And we find that there's a sweet spot in terms of the number of detections, maximal number of detections you can make. And that's somewhere around 400 and 900 or 400 to 1,000. And that seems like the best reason or to focus on that area. We find that acquiring data up above that range can be useful in certain circumstances, though, if you need to measure specific peptides. So knowing some things about our experiment, there are several different things that we can calculate, right? So if we know something about the average peak width that we expect, say it's 25 seconds, which we can determine looking at older DDA-based data, we can start to back calculate what we would need to work with how the instrument should be set. So if we're expecting 10 points across the peak and trying to scan in this 400 to 1,000 MZ range and calling that fixed data, we know something about the chromatographic conditions, that we expect peaks to be 25 seconds. We know that our instrument scans at a specific maximal rate, say 10 hertz on a QE or a QEHF. We can actually determine what the cycle time should be and the number of scans and the isolation width ought to be to acquire the optimal data for this experiment in at least regularized windows. And so we've actually pre-calculated for a bunch of instruments what the optimal settings should be, as well as what some good windowing settings should be for normal windowing methods across these ranges. And so these are available in this PDF for you to download and just use it as a quick start guide to get started, get going quickly, but at the same time, you should optimize these for your instrument platform and your chromatographic setup. So when you go to configure this in your instrument, you'll open up your method editor and select to build a DIA experiment, and you'll need to set a bunch of properties as well as set for the inclusion list where these precursor window centers are actually going to lie. And it should be as simple as copy and paste into the method editor. Looking at some of these properties of the method setup, you'll again going to need to set a fixed charge state. We usually recommend 2 to begin with, because most peptides we find that are tryptic are charged 2. You're also going to need to set a fixed collision energy, and this is going to be optimized again for the average peptide that you're interested in. So here we're usually going to try to match the ion accumulation values to the resolution of the instrument so that your maximum ion and jet time is fitting with the amount of time that it takes to acquire a scan, an MS2 scan in the Orbitrap or the top instrument. You also need to set a loop count, which would be really how frequently you expect to find MS1s in your experiment, and then your window width, which will be set for the isolation scheme that you've decided upon. So there are a bunch of optimizations that you can do to make your DIA experiment a little bit better, and one of them that we recommend is thinking about overlapping or staggered windows. So in the traditional sort of DIA approach, you would again acquire a precursor scan followed by a bunch of fragment scans, and then repeat that process over and over again. With the staggered or overlapping window concept, we actually take those centers and then shift them over every other scan and then add in an extra scan. Here, while we do get off-shifted every other duty cycle, we get the slightly different fragment scans, we can actually use mathematics to deconvolute our fragment scans to be half the width of what they were. So instead of looking at 24 MZ wide windows, now we can acquire data with 12 MZ wide windows just using effectively a mathematical trick without having to buy a new instrument or run the instrument much faster or harder than it was meant to be run. So this overlapping trick, I think, provides really excellent results. So for example, this particular peptide, this ASAP peptide, falling around 50.5 minutes, has a lot of background noise when you're looking at it with the 24 MZ wide DIA, 20 MZ wide DIA experiment. And this just happens to do with the number of ions that fall into the background of that analysis. However, if you do this 20 MZ overlapping method, so that's where you shift over every other scan and then do mathematical deconvolution, we can actually get the amount of background noise down substantially. Now, there still is going to be some fragment interference, say, for example, this pink peak, but for the most part, we can actually trim it down substantially. And if you compare this 20 MZ overlap DIA to 10 MZ DIA, we actually see that they're quite similar, such that even that pink interference is reproducible. This gives us a lot of hope that this approach actually really does get us for free half of, or effectively being able to measure half of the isolation width as we were doing before. So 10 MZ wide windows instead of 20 MZ wide windows. There are other strategies to optimize window widths or window parameters too, and another one that's been pioneered by the Aebersold lab is called variable width windows. Here, instead of acquiring the same precursor isolation width window over time, over the duty cycle, you might acquire a fairly wide fragment ion scan at the beginning, followed by several narrower fragment ion scans, and then down at the end where you expect fewer peptides to be, having, again, wider fragment ion windows. This approach definitely can get you much narrower windows overall, and yet still be able to acquire peptides in the range from 1,000 to 1,200 MZ overall. And potentially this can get you some additional peptides as well. Typically, we tend not to use this strategy primarily because we feel like, for the most part, the peptides that we see in that 1,000 to 1,200 MZ range, we can typically usually see a higher precursor charge state in the lower 400 to 1,000 MZ range instead. And so we prefer just to acquire higher quality data in that lower range. One thing that's important is that variable width windows and overlapping windows really don't go along together without some major mathematical lifting, and so we don't recommend doing that approach. So another important thing to consider is adding potentially windowing margins onto your measurements. And this has to do with the transmission efficiency of quadrupoles. This will allow potentially older instruments to be used for DIA as well, ones that don't have quadrupoles that are designed specifically for DIA. So instead of acquiring fragment ion scans where the windowing boundaries abut each other, we talk about increasing these ranges by just a hair, maybe half a Dalton on either side, and adding that onto the ends of each side. And the idea here is that you basically try to make it such that all of the peptides end up in the center of that transmission, that optimal transmission efficiency range, at the expense of being able to include a little bit of additional precursor isolation noise from other peptides, so other peptides that are co-fragmenting from those margined error areas. Finally, an important other consideration is this idea of optimized window boundaries. And here the idea is that peptides are made up of all of the same stuff, hydrogen, carbon, nitrogen, oxygen, sulfur, and that we can take advantage of sort of dead zones where peptides don't exist because there are only so many masses that you can make up with those mass defects from those particular combinations of atoms. And so here I've just plotted from 600 to 610 all of the different peptides that are found in uniprot that are +2, +3, +4. And you can see that there are clearly sections where you just don't see any peptides. And if you tune your windows to fall in these specific ranges, you can actually do away with the need to acquire peptides with those wide margins because you're essentially setting the windowing boundaries where there aren't peptides anyway. One final consideration that I think you should think about is this idea of gas phase fractionation. So what do I mean by this? So typically a DIA experiment would acquire a precursor scan and a 25, 24 MZ wide windows, something like that. But potentially, if you had enough sample and enough instrument time, you could break this up into multiple acquisitions. So in the first acquisition, you might acquire the range 400 to 700 instead of 400 to 1,000, but with half the size of windows. And in the second acquisition, measure the other half from 700 to 1,000. This can be a really powerful way of increasing or decreasing the width of the windows simply just by throwing more instrument time or more sample at the problem. And I want to show you some idea that's actually a little bit out of the box on this idea. So instead of acquiring just 2 gas phase fractions, what if we were to break this down even further? So acquire our first fraction from 400 to 500 and 500 to 600, then 600 to 700. So 6 total acquisitions, but make these acquisitions so that they're 4 MZ wide windows. Now if we use the overlapping or staggered approach, we can effectively derive 2 MZ wide windows. And now when you think about it, we've measured using a DIA something that is approximating PRM level precursor isolation, yet we're doing targeted proteomics with PRM for every single peptide in the 400 to 1,000 MZ range. This is an extremely powerful strategy to be able to mine very deeply into a proteome. Again, at the exception that we actually have to use 6 times as much sample and burn an additional 5 acquisitions. That said, we can leverage this idea, and I want to show you this through a way of analogy. So this is really kind of the promise of the idea is encapsulated in this Google gigapixel camera image. So with DIA, we expect to be able to extract out every single person in this picture of, in this case, the presidential inauguration, and be able to know exactly who attended the inauguration. Now, if we look over in this corner, we might see a picture of Barack Obama smirking, and over in this corner, we might see a picture of the now President Trump giving his inauguration address. And if we were really wanting to try to detect these, we could match these to known people, known pictures of these people already. But the reality is, because of all the compromises we've talked about, we really don't have this level of precision in the measurements. And so really what we're trying to do is compare this picture of Barack Obama from a query data from a spectral library that's acquired at a totally different time, maybe Obama's wearing a different colored tie, to this picture of Obama at the inauguration and try to pick him out. It becomes a much more difficult problem. So the way in which we can leverage this gas phase fragmentation approach is through what we call chromatogram library acquisition. So typically we might acquire n quantitative samples, where this would be 40 or 50 or 100 different quantitative samples that we would want to measure from an entire precursor isolation range. We would analyze these with scaffold DIA and try to quantify these peptides. So that can be done, but what we're trying to do is take a sub-aliquot off of the top of each one of these samples, or a representative fraction of these samples, pool of those samples, and then make a detection sample. And this detection sample, we're going to focus not on quantitation, but on making an accurate measurement of every single peptide that's in that sample. So we'll do this gas phase fractionation approach where we'll measure from 400 to 500, and then 500 to 600, 600 to 700, and on. And then analyze that with scaffold DIA, either using another spectrum library or using a FASTA database. And then create what we call an on-column chromatogram library. Using this specific representation of how the peptide looks in terms of its fragmentation pattern and its retention time, we can much more easily pick out what those peptides actually are. So that's kind of like thinking about this gigapixel camera picture, where the picture itself might be from 400 to 1000 MC, and we're breaking it up into 6 different sections and taking a deeper picture, just like the gigapixel camera does. So for that region from 600 to 700, it's much easier to find President Obama in that picture and represent that as a chromatogram library image of President Obama, and then match him to this query data. Maybe he's wearing a different tie this time, maybe his hair is a little bit whiter, but we can still make a reasonable detection of him. And now that we know this is what President Obama looks like in our samples, it's much easier to query him against our data based off of this new chromatogram library detection, where his picture is tuned for what he looks like on that day and that time. So to recap on all of the stuff that I've been talking about, we've compared DIA to DDA approaches, where DDA, you typically let the instrument decide what peptides you want to sample, and then measure them in different peptides at every single duty cycle. We can contrast that to sort of typical normal DIA, where you have much wider precursor isolation windows, yet at the same time you can still measure the same precursor isolation window range. Or a reasonable precursor isolation range. We talked about some different parameters that you might want to focus on when setting up a DIA experiment. So why would we want to pick 6 to 8 points across the to represent the peptide? Why do we need to use 400 to 1000 MC wide windows? Or why do we want to set 24 MC wide windows to begin with? And why we would potentially want to make other choices than these depending on our chromatographic setup or our instrument speed or that sort of thing. Finally, we talked about some additional approaches that kind of improve upon this idea. First one being overlapping windows, where we shift over every other duty cycle scan. Variable width windows, where we'll measure different size precursor isolation windows at different points in the MZ range. And this gas phase fractionated DIA experiment, where you might want to try to dig as deep as possible to determine the maximal number of peptides in the entire experiment. So with that, I'd like to conclude, and thank you for participating in this lecture.